So let's look at some examples where we actually apply the sum and difference identities. For this first example, I want to rewrite an expression using the appropriate identity, or in other words, simplify something that looks like this. Here I have the cosine of 180 minus theta, and I can use the difference identity for cosine to rewrite this so it looks like the cosine of the first, the cosine of 180, times the cosine of the second plus the sine of the first times the sine of the second. And we're going to simplify that because I know that the cosine of 180 is actually negative 1 and the sine of 180 is 0. So what happens is this section over here becomes negative cosine theta, and then this just becomes 0. So that's the answer when I simplify it. Let's try one more like that. The cosine of 90 plus theta. So again, we're using the sum identity for cosine, and it looks like the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second. Again, we want to simplify this. I know that the cosine of 90 is 0 and the sine of 90 is negative 1. So this portion over here disappears and the right hand side becomes, and it's not negative 1, sorry, the sine of 90 is 1, but this side over here becomes negative from that sine, 1 times sine theta, which is just negative sine theta. Okay, so really when you're given a problem like this and you use the identities that we've been talking about, we're kind of using them to make these two angles into a single angle, which we might want to do when we're solving equations. So this next example we're going to look at asks us to find the sum of two angles given cosine of s and the sine of t. So the first thing I want to do when I look at this is, well, what does the cosine of s expand out to be? What makes up the cosine of s plus t, or the sum identity for the cosine? And it looks like the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second. Now there are 4 pieces to this identity, and I'm only given 2 of those pieces. So I need to use one of 2 methods to come up with the cosine of t and the sine of s. One method that we've used in the past would be to use the definition of trig functions. That's where I break down x, y, and r. So here when I'm looking at angle s, I know that x is negative 1. I know that r is 5, and therefore I can calculate what y is. Okay, and those all come from the fact that I know that cosine is the ratio of x over r, and r is always positive, so that means that x must be negative in this case. Or I could have seen that we're in quadrant 2 and cosine is negative in quadrant 2. But I need to solve for y. So I do that using the Pythagorean theorem, which says x squared plus y squared is equal to r squared. And if I solve this for y, I see that that's really r squared minus x squared. So I just rearrange this formula. Plugging in, I would recognize that this is going to be 5 squared, which is 25, minus 1 squared, which is, or negative 1 squared, which is 1. And in other words, that's the square root of 24. Simplifying that just a little bit further, this becomes 2 square roots of 6. So what perfect square factors go into 24? Well, that's 4 times 6, and the square root of 4 is 2. So I know x, y, and r for angle s, and now let's do the same thing for angle t. So here, I'll just use a different color. Over here, I know that y is equal to 3, r is equal to 5, and x is going to be equal to 4 because that's a 3, 4, 5 triangle. I also know that because when I use my definition of trig functions, I know that sine is y over r. Sine is positive in the second quadrant, so that's how those are made up. So I have everything I need to come up with the cosine of, the sine of s and the cosine of t. So let's just write those down. So down here, I know that the sine of s is going to be y over r, which is going to be 2 square roots of 6 over 5. And I know that for angle t, I'm looking for the cosine of t, which would be x over r, which is 4/5. So I now have all 4 components of my identity to be able to fill in. So let's just scroll down and we'll fill that in. Remember that the cosine of s plus t is the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second. We know that the cosine of s, we were given that to begin with, and it's above there, but the cosine of s is -1/5. The cosine of t is 4/5 minus the sine of s, which is 2 square roots of 6 over 5, and the sine of t, which we were given in the problem above, is 3/5. So let's just multiply. Remember, when we multiply fractions, we multiply numerator to numerator, denominator to denominator. So this looks like -4 over 25. And then over here, we have 2 square roots of 6 times 3, which would be 6 square roots of 6 over 25. So this looks like -4 minus, let me write that down this way a little bit, 6 square roots of 6 over 25. This is an acceptable solution or an acceptable answer. You could have combined the numerator, so it looks like -4 minus 6 square roots of 6 all over 25, and both of these are the same solutions. So that's one of the methods that I'm going to show you in this video, and that was method 1, using our definition of trig functions. Now this last example is doing the exact same thing. I've just chosen to practice this problem one more time, this time being given the cosine of s and the cosine of t. So I kind of want to challenge you to stop the video, practice this problem on your own, and then let's see if we get the same answer. Okay, so let me explain what I've got here for you. I was asked again to find the cosine of s plus t, given the cosine of s and the cosine of t. Using the definition of trig functions, I know what x, r, and I can figure out what y is for the angle s. And I did the same thing over here using the definition of trig functions, x, r, and y for angle t. Once I have that, I know I can, again, use our definition of trig functions to figure out what the sine of angle s is, which is y over r, and the sine of angle t, which is again y over r. Now that I know what all 4 components are, I can plug it into my identity, simplify. So here I have plugged it in, simplify, and you find out that it's -36 over 85. The second method to do this would be, instead of using my definition of trig functions, or which is the x, y, and r, what if I used trig identities to solve for my missing components of sine s and sine t? So using the Pythagorean identity for both angles, and remember, I'm given the cosine of s, so I would replace the cosine of s here and simplify. And I would do it again over here for the cosine of t. And when I do that, Simplifying both of these equations separately, of course, you find that you get the sine of s is negative 15 over 17, and the sine of t is negative 4/5, which is the same thing that we found using the previous method, or method 1. Once you have, again, all four components of the identity, then you just do the same thing. You would plug it into the expanded form of this and simplify.